Is the mic on? Okay, great. Cool, we'll start. So I'm Francis, and this is Virag. And we're here to talk to you about scaling to millions of regions in HBase and why that matters. So this talk will be basically break down into two parts. I'll be talking about sort of why region size matters, and then Virag will be talking about the changes we've done so that we can actually scale to millions of regions in HBase. So just a quick overview with HBase at Yahoo. So there's this thing called the Yahoo grid at Yahoo, which is essentially the Hadoop hosted multi-tenant service at Yahoo. So it's essentially a hosted service of the Hadoop technology stack, and HBase is a part of it. So HBase is used mainly for, or only for off-stage processing. You can do batch processing over it through Pig, through Hive. Those things we support. You can also use it through near real time using Storm or any custom application you use. Of course, we use it to store a lot of data. And it's just like the rest of the grid, it's also a hosted multi-tenant service. The things we care about in terms of HBase, probably same as everyone else, throughput, latency, availability. But something we probably care more about than other people is scale. So we have a lot of experience at scale. We have 6 multi-tenant HBase clusters. The largest one is around 700 nodes. It has more over 100,000 regions. So we actually are running at scale already. But the thing is, it's not enough, right? So even our multi-tenant clusters now are still growing. And not only that, but we also need to scale to petabytes of data supporting near real-time workloads. So sort of this is where sort of our problem is coming in. So we actually already have scaled supporting a use case which has a single table, which is 2.3 petabytes of data. It's mainly a batch processing workload. And so we ran into a lot of issues because we started with 80 gigabyte regions, because we wanted to reduce the number of regions that had to be deployed on the cluster. And so we eventually cut it down to 20 gigabytes. So this is sort of what made us start thinking about how we can scale to have smaller regions, because large regions are really not good. And so I'll be talking about the issues we've seen and the things sort of we thought about when we were worried about region size. So first, let's quickly go through what a region is. So a region is a subset of the table's key space. So it's essentially a shard of the table, a portion of the table. And a region essentially is a few things. So it's the unit of work, right? So depending on what you're using, it's usually a unit of work. It's run in a region. It's the unit of load distribution. So it's what's spread out on the cluster, and it's what region servers are serving. And it sort of defines the availability for your table or your data set. If one region is offline, then a certain percentage of your data is not online. So let's see, for unit of work, what that means is that, for example, MapReduce, when MapReduce runs, it needs to calculate what's called our splits. And splits determine the amount of work that gets distributed across tasks. And for HBase, the splits are calculated basically on the number of region servers. One split is, region. One split is one region. And so what that means is that your level of parallelism is determined by the number of regions you have in your table. It also determines the compute time for a given task, because the larger region you have, the longer your task will run, which also determines the recovery time. For example, if the task fails, then you'd have to rerun and reprocess all that data. And then, of course, it also defines the amount of skew you have. The larger regions you have, if your data set is not uniform, then potentially you have really small regions and really large ones. And the time it will take for your job to finish will be determined by the largest region. So here, I just have an example where you essentially have a couple of tasks. One of them has a larger region. And basically, the job will take much longer because of that one task. So apart from MapReduce, there's also things in HBase that work on regions. One of them is filters. So if you run a filter, that filter is, the scan is processed on using that filter on a given region. And if your filters are really sparse, then what that means is that your scan will not return until it actually found a match. And worst case, if there is no match in a region, it will not return until it's processed the entire region. So what you get is scan timeouts. And so what happens there is no matter how many times you retry, and as long as the data does not change, then you'll just keep on failing. And you'll be wondering why your MapReduce job is failing. And it's probably because the filter, the filter that's trying to match doesn't find anything on the region. So in the previous use case we used, we essentially had one 80 gigabyte region which took like 30 minutes for the scan to finish because it could find no match. That was part of the reason why we started cutting down the regions. Also, even custom applications that want to process a table will have to figure out a way of dividing the work across workers of its own. And most of them will decide that regions are probably the best way to go. And so that's sort of how this sort of motivates why, from a unit of work perspective, why you'd want smaller regions, because you'd have better control parallelism and better control of like the recovery time. So let's talk about load distribution. As I said, the size of region determines the load that's balanced across the region servers. So what you have is essentially that the larger the region, then the less granularity you have. So if one region is hot, even though it doesn't matter, how many servers you have, it will only be one region server that's serving it. So therefore, basically that server will potentially be overloaded. Another thing is that another thing to keep in mind is that you also have tasks, as I mentioned earlier, that the tasks, the number of tasks that run is determined by the number of regions. So if a region server has more regions than the others, then it will have more tasks running against it. So either way, if your server's overloaded, then it doesn't matter, right? Like you will be only as fast as your slowest server. So it's important that you have good balance. Another thing is that if you have, so one downside to having too many regions is that you might have too many tasks running at the same time, and that too may also overload the server. So for that, you can, there's this enhancement in MapReduce where you can limit the number of tasks that are running, and so that you can control the load that is sent to the region servers. So so this is sort of one downside to having smaller regions, but it's not really a downside because you just need to control the amount of parallelism you have. So it's easier to control, roll up parallelism than to actually break it down. So another thing I'd like to talk about is that affects availability is compaction. So compaction is essentially an optimization for reads. So in HBase, when you write data, it actually ends up in potentially multiple store files. And those store files are essentially combined to actually produce the row or like the set of rows that you're trying to request for. So what that means is that worst case, if let's say I had 4 store files and I wanted to access get all the cells for a given row, I might have to read all 4 store files. And so that requires at least 4 disk seeks. So that would be pretty expensive. And so that's where compaction comes in. Compaction will essentially read all the data for a given set of store files and then rewrite it as a single file. So what that means is that you only have now to do one seek to actually get that row that you look for. The downside to this is, because there's no free lunch, is that you're contending for the same I/O you're actually using to actually read the data. And so this is where sort of region sizes come into play, because the more store files you have to compact, the larger they are, then the more I/O you need to run compaction. And so this is where region size comes in. The larger the region you have, the larger the compactions you will potentially eventually have. Other thing is when you run compaction, it will also cause cache misses as the blocks that were cached were invalidated because the new files are the data now the rows that contain your data are now contained in new blocks. Other thing to keep in mind is write amplification. As I mentioned earlier, the larger the files, the more row keys you have. The larger the regions, the more row keys you have. So what that means is that there could be potentially a very small set of rows that are updated frequently, and then you'd have to compact all the data even though it's only the few rows that are updated. So what that means is you're wasting I/O rewriting data that was never changed. So this is again another reason why you probably want small regions, so that you avoid write amplification and not have to waste I/O when you don't have to. So let's take a deeper look at regions. So a region is composed of store files, as we said. And store files are actually stored on HDFS. So what that means is that a single file is actually broken up into a number of HDFS blocks. And so what that means is that when you actually read a file, the data actually may not reside on a single contiguous space on disk. It will reside on a number of blocks, which could be on different set of disks depending on the number of blocks you have. So what that means is that when you do a scan for a large region, you'll actually potentially have to do a number of seeks equal to the number of blocks that you have, best case. And so it doesn't matter whether you have multiple regions or a large region. If they have the same number of blocks, most likely the performance is the same. So this is sort of why larger regions, it doesn't really matter as much. So having said that, what's the size then? So if you think about it, there's the general rule to think about it is you want it small, because there is nothing to gain when it's large. And then how small should it be? It should probably be as close to an HDFS block size as possible, because as I said, you'll have to do seeks anyway if the region is larger than the block size. Having said that, there are cases where size doesn't really matter. But I'm hoping that given what I presented, that you guys will be able to sort of dissect and figure out whether your use case actually sort of requires smaller regions or larger regions, sort of help you decide. And having said that, I'm turning the floor over to Virag, who's going to talk about all the cool stuff, the enhancements we've done.
Thank you, Francis. As Francis said, we wanted to go with smaller regions. But now, if we want to go with smaller regions, at the same time, we also want to scale to petabytes of data. So how do we do that? So we increased the number of regions in the cluster. So we started experimenting with 1 million regions in a test cluster. Master is the key component here because all the region management is controlled by master. Master is responsible for assigning the regions. It's not only that, it's also responsible for doing admin operations like balancing regions across clusters, enabling table, disabling table, and so on. So master scalability is very important. A region has a metadata. This metadata could be the mapping of region to region server, what state the region is. All this metadata has now suddenly increased because now we have more regions in the cluster. And this metadata is stored in a meta table, so meta table needs to scale too. HBase can scale, but the underlying file system, which is HDFS, also shouldn't be a bottleneck. Zookeeper is used by multiple components within HBase, and that also needs to scale. Region servers are the one who are going to host the actual regions. So even if you have thousands of regions on a region server, that should not be a problem. So let's go through a quick overview of how region assignment works. As I said earlier, master is responsible for orchestrating the region assignment, but the actual region metadata, which is the region mapping, which is basically where the region is located, what state the region is in, what was the previous state of the region, all this region mapping is tracked by 3 components. One is master memory, other is the meta table, and it's also stored in some of the Zookeeper Z nodes. Let's take a quick example. This is a pretty simple region transition example. In step 1, you can see that master is trying to assign a region to the region server. The region server, once it has processed that request and the region is opened, it sends a notification to the Zookeeper. Master now receives a notification from the Zookeeper in step 3, and it updates its in-memory state. And in step 4, the region server updates the meta table with the new region location. A note here is that 3 and 4 could happen in parallel because they're asynchronous. So now when we run ZK assignment and try to assign million regions using that scheme, what are the things that we see? We see that even though the previous diagram might look that it seemed very simple, the actual ZK assignment scheme is very complex. Because there is this 3-way communication where the region server doesn't directly talk to the master. It uses Zookeeper as a means of transmitting data to the master. And there could be all sort of split-brain-ish problems you can think of. For example, the region server could be updating meta, but the master gets a delayed notification from Zookeeper. Or maybe the master just dies before even it gets a notification. So in order to maintain the region state integrity across all 3 components, across Zookeeper, master, and meta, it's a difficult task. There's one more issue here, which is Zookeeper is not only used for coordination, it is also used for storing the transient region states. So to just illustrate with an example, we could have, let's say, million regions getting assigned, and just in the middle of an assignment, the master goes down. So the backup master will come up, and it will try to read from Zookeeper and try to figure out which were the unassigned regions. But in order to do that, it has to read a Z node which has those 500,000, let's say 500,000 regions were unassigned. So it goes to that Z node, it tries to read that Z node which has 500,000 regions, which has basically 500,000 entries under that Z node. And if you try to do an LS on a Z node with 500,000 entries, it's not going to even finish. It will just be stuck forever. In my experiment, what I had seen is like there are only 100K entries under a Z node, but still the LS operation took 45 minutes to an hour to complete. So using Zookeeper as a store for region states is basically an anti-pattern. It should only be used for coordination. So what are the enhancements that have happened in the community? One of them is ZK-less assignment. As you can see in this diagram, there is no Zookeeper involved now. The region server directly sends an RPC back to the master. The region server sends an RPC to the master updates the meta table, and then only the region transition process can complete on the region server. So the good thing here is that for any region transition to finish, master is involved, and master is in control, which makes things simple. And for the previous problem where in the ZK assignment scheme where you had to read 500,000 entries from a Z node, here now all metadata is stored in only meta table. And doing a scan on a table is way better than doing an LS on a very big Z node. One of the other problems we had seen with assignment is in general that you have multiple assignment threads trying to do assignment, but they all try to obtain one global metadata lock, which caused CPU contention, and I saw the CPU utilization going to almost around 40%. What we did was, instead of having a single metadata lock, all the assignment threads will now obtain region-specific locks or more granular locks, and that avoided the problem, and that also reduced the CPU utilization. Here's a comparison between ZK assignment and ZK-less assignment. With Zookeeper, you can configure the server in 2 modes. One is forcing is equal to yes, and forcing is no. Forcing is yes means the transaction logs will be persisted to the media straight away, while with forcing is equal to no, it can happen asynchronously. So with forcing is equal to yes, the performance is terrible, right? It takes more than an hour to finish. And you can, and with ZK-less, there is not much performance degradation compared to even ZK assignment with forcing is no. In the whole assignment process, the master is writing to the meta table. It's writing the metadata to this meta table. And what we had seen is once million regions are assigned, and you go and take a look at the size of the table, even after doing major compaction, the size of table is 7 GB. And master cannot split. So you will have all problems that a large region will have. And Francis already mentioned all the problems that a large region could have, larger compactions. You rewrite, small data changes, but a lot of data needs to be rewritten during the compaction. Longer failover times, because a big meta region goes down, it will take some time for the other region server to bring it back up online. Also, the scanning times will be long. So we decided to implement split meta, and now we'll get all the benefits of smaller regions. Now meta is just like any other user region. So your IOPS will be distributed across regions. Metas are small enough so they can be cached on the region server, so your reads will be faster. The scan times will be shorter. The compactions are smaller and much more distributed now. This is very preliminary experiment where we compare single meta versus split meta, and we are trying to assign 3 million regions. Here you can see like there's significant performance benefit, even though we haven't tuned the meta sizes. We just kept the meta to be 200 MB, and the meta is split across 10 servers, where each server is hosting around 5 to 6 metas. We could definitely do better here by varying the meta region sizes. Even before HBase starts the assignment process, it needs to write the region files onto file system, which is HDFS. And in the current layout, you have one table directory, and you have all the region directories under that table directory. What we saw was that it takes quite a while for this whole process to finish if you have a million, if the HDFS is creating a million files under a single directory. Also, there is a name node limitation. It's a hard limitation where it can hold, where a single directory can hold maximum 6.3 million files. And this limitation comes from the fact that when the FS image is actually encoded as a protobuf, and protobuf default limit for default message limit in protobuf is 64 MB. This is a graph of throughput for the name node creation file operation request over a period of time. And as you can see, the graph is basically decreasing logarithmically. And the reason behind this is that name node internally uses an array list to hold all the region directories, all the region files under a single table directory. So the problem with array list is twofold now, right? One is that as soon as it reaches a max capacity, the contents of that array need to be copied elsewhere. And as you can see, with more number of entries into that array list, this problem is going to be more acute. Also, the array list needs to be sorted, and in order to insert an element in the array list, you need to do some sort of operation like a binary search, which will have some complexity associated with it. So we decided that we will try to implement a very simple approach. This is a bucketing approach. Instead of one table directory hosting all the region directories, you will have buckets, and within these buckets, you can have your actual region directories. We call the table as Humungous table. Just to give an example how this works, you have a region hex string. You take first 3 letters of that hex string, which will give you 16 raised to 3, which is 4K buckets. And now you have 4K buckets, and each bucket can have 250 files, which amounts to total 1 million region files. And this is now the graph for the throughput for the create file ops. And you can see that the throughput is constant over a period of time. The performance results, well, we compare normal table versus Humungous table. And as you can see, even with 1 million regions, you get 5 minutes benefit. With 5 million regions, the benefit is significant. 10 million regions do not even finish with the normal approach due to the protobuf issue that I mentioned earlier. But with Humungous table, it only takes it takes 3 hours to finish. So thank you for listening. Questions?
Questions? Okay. Yeah, go ahead, the mic.
In the previous slide, what does, like when you talk about normal size and humongous size, can you put some numbers on those?
Which one, this one?
Yeah. When you say normal table and the humongous table,
So sorry, the normal table is created with the normal approach, the first approach, where you have one table directory and all the region directories are under the table directory. This is the default layout. So before even, so the first thing HBase does is when you issue a create table command, it writes the table directory into the file system, and then depending on the number of regions, it starts writing all the region files under, region directories under the table directory. This is the default approach. But let's say you have 1,000,000 regions and you have to write all this 1,000,000 region directories into that table directory, which will have problems. And the humongous table is the one where we, instead of having one directory hold all the region directories, you basically have subdirectories, which we call buckets. Within buckets, you can have your actual region directories.
Question, when you talk about, I'm pretty new to HBase. When you talk about increasing or decreasing your region size and increasing your number of regions, is HBase smart enough to just take the existing data and go move it all around? Or do you have to drop everything, make those changes, and then re-ingest it so that it can distribute it in the appropriate places?
Right, so HBase does splits automatically. That's when your region gets beyond a certain size and it splits it based on the mid key. And so by default, it's configured to split at 10 gigabytes. And for cases where you sort of care more about latency and your write throughputs are really high, you probably want something smaller. So that's essentially just a configuration change, and you just need to restart your servers to get the change to take effect.
And so will it affect the existing data, though, or like just future data that comes into the system?
So your regions will be split. So whatever data is in the regions, which is basically existing data, will be rewritten as part of those new regions that are created.
So I have two questions. My first question is how many regions you have in each of your region server?
Oh, okay. I'm not sure. I think the biggest one is like maybe 1,000, somewhere there. I can check, but yeah, somewhere around 1,000 is probably the most.
And do you think having many regions in a single region server will affect the efficiency of the man store? Because like you allocate a certain size of memory to your HBase, and if you have many regions, each of your man store will be really small, and it might have a lot of flush when you have a lot of Y to your region servers. So, yeah.
Right, that's right. So yeah, the more regions you have, the more your mem store is split across. Your mem store memory is split across the regions. So yeah, it's a matter of tuning essentially. So it's a trade-off of like larger regions, more compactions, more write amplifications, or like small regions. So if your data is sort of Zipfian, it's like, it's not uniform, then it makes more sense to have small regions because those other regions will probably not have any writes, right? So you will essentially have less amplification and you probably need less memory. I mean, sorry, the same memory should be enough.
Is there a separate syntax to use the humongous table? And which version of HBase is this available in?
So the first question, it's a very simple way when you do create table command, and you can just pass a flag to the table descriptor saying the table is humongous. By default, it will be the default approach will be the normal table approach. And to the second question, the code still needs to be open sourced.
So we're working in the community. I think Virag referenced the Jira number, and so we're working with the community to get all of this out. They're on board with like splitting meta and growing to that much. So it's just a matter of like back and forth. So in terms of the version, it's not clear. It's probably like maybe when it hits trunk, then it'll be clear at what real version it will come in.
So that means that if we've got an existing HBase system and we decide to go to a lot more regions, we'd have to recreate the table, or will that automatically get rolled in?
So I guess, so your question is essentially if I want to make it humongous, how do I do that sometime in the future? I'm sure it's not that hard to sort of do the migration, but your table will likely have to be offline for that to happen. This is just offhand thinking about it. There should be a way to migrate it to humongous. Your table will likely have to be offline. And you only have to consider using Humungous at this point. From what we notice is essentially table creation is what takes the longest. So if you already have a table and you don't think it'll reach like somewhere around 6 million, then you don't really need to use Humungous.
All right, thank you.
I got a question regarding the table you mentioned just now. It means it seems like you have thousands of regions in one regional server. It's only for one table or all the tables in our HBase?
100,000 regions. So there we have one table that's over 100,000. So it's 2.3 petabytes of data. That's over 100,000. The region size is around 20 gigabytes. So that's one table. We do have a cluster that has a lot of tables, and the sum of all the regions they have on that cluster is over 100,000 too.
Oh, just now you mentioned that you have in one region you have the most number of region server is 1,000. Is it just now?
In one region server, the most regions it has is 1,000.
Yes.
Yes.
And my question is, do you turn on the auto balancer to do the balancing? Like if I got more region in this region server, the balancer will just transfer this one to somewhere which have less traffic.
Yes. Yes.
Then how do you suggest us to turn it on, or we just leave it closed, disabled like that?
I see. So the way it works with us is our clusters are multi-tenant. We're using this sort of feature where you can pin a set of pin a table to a set of region servers. So let's say I want this table to be run on only 10 servers, and so sort of that's how within that 10 servers the regions are balanced, but relative to the rest of the cluster, then it's not. So this is sort of another feature, yeah, that we have.
Okay, thank you.
Nice share and thank you. And I have a question here. So for the hierarchical region directory feature, is there already a Jira in the community?
No, I don't think that one has a Jira, but there'll be one soon. It'll be probably part of the parent Jira that we have.
Okay. Then another question here is that for this feature, is the rolling upgrade still available? I mean, what if a region server crashed when I rolling upgrade the server, then it crashes, then another region server might not recognize the directory.
I see.
Right?
Right, that's correct. So that's why I mentioned that potentially if the upgrade needs to be happened to Humungous, then yes, you might have to take the table offline while you do the migration and then bring it back online.
So then maybe a rolling upgrade is not possible then, right? That's a problem, right?
It's probably possible, but inefficient. You can try and look at the directory. If you don't see it in that hierarchy, then maybe you'll try and look for the bucket. If you see the bucket, then you can try and read it, right? So there's probably ways around it.
There's still some work to do, right?
Yeah, some work to do, yes.
Okay.
Get it working first, and then, look at actual migration.
Okay. Thank you very much.
Cool. I guess that's it.
Thank you.
All right, thank you.